All right, so here's the first Clausius-Clapeyron calculation or example. All right, carbon disulfide has a normal boiling point of 46 degrees Celsius. What does that tell us? The word normal boiling point means that you are at 1 atmosphere or 760 millimeters of mercury. So we know that this is associated with 760 millimeters of mercury, okay? Delta H of vaporization is 26.8 kilojoules per mole. What is the vapor pressure of carbon disulfide at 35 degrees Celsius? So the pressures, these are the vapor pressures. And what we're going to do is we're going to say that this is our T1 and this is our P1. Okay, notice they didn't give us P1, but we understood that from the word normal. Normal boiling point, that's what it is. All right, means we're at 1 atmosphere, which is 760 millimeters of mercury. All right, so we're going to plug everything into this. So this is my P1. I'm going to put 760 here. Okay, the R value is going to be given to you, and that is 8.31 joules per mole Kelvin. Okay, the delta H of vaporization has been given to us. Since this is in joules, let's go ahead and switch that to joules. So instead of being 26.8, it's going to be 26,800 joules per mole. That way our joules cancels, mole cancel. Now, the temperature has to be in Kelvin. So this is my T1. We'll take 46 plus 273, and that is 319. So this is T1, this is P1. T2 is this guy, so 35 plus 273, that is 308. Okay, let's put that here. Okay, now you just have to know how to use your calculator to deal with logarithms. Before you even touch the logarithm buttons, what you need to do is do the math on this side of the equation. So do this, 1 divided by 319 minus, open parentheses, 1 divided by 308, close parentheses, press equals. So do the math here, and then multiply it by 26,800, and then divide by 8.31. Get a number on this side first, guys, okay? Once you get a number on this side, then you're going to have to figure out how to get rid of this button here. And what you want to do is basically take the anti-log on this side, so it'll get rid of this, and then take the anti-log here. Long story short, the number you're going to get on this side, let me erase all this, is going to be negative 0.361. All right, so I'm going to erase this. You already have the problem in your notes. So this side is going to be negative 0.361. And this is equal to natural log of P2 over 760. So what you have to do is take the anti-log of this, which is basically e to the x. That way we get rid of this. So I need the e to the x of this side now. All right, so get your calculators. Press that anti-log button, or the e to the x. Can you see where the ln is? It's the thing that's right on top of it, okay? So it's like basically e to the x and then minus 0.361. All right. Once you do that, you then multiply that number by 760 and you will get your answer. All right. So go ahead and do that. I'll do it to just double check here. Minus 0.361, close parentheses, and then I'm going to multiply that by 760, and you get 529.7, which would be 530 millimeters of mercury. That's your answer. Okay, good. So that's one type of problem. We're ready to move on to another type. This one, they're going to give us both temperatures and they'll give us both vapor pressures, but we need to find delta H of vaporization. Okay, so we're still using Clausius-Clapeyron equation. Okay, need to clean this board off a little bit. So the vapor pressure of ethanol, vapor pressures, this is plural, of ethanol are 100 decimal millimeters of mercury and 760 millimeters of mercury at 34.9 degrees Celsius and 78.4 degrees Celsius, respectively. Which one's the boiling point of ethanol? You can tell from this, right? 760, 78.4. So the normal boiling point of ethanol, 1 atmosphere, 78.4 degrees Celsius. Okay. Question is, what is delta H of vaporization of ethanol? So ln P2 over P1 is equal to delta H of vaporization over R, 1 over T1 minus 1 over T2. All right, you know the drill. We're going to plug and chug, and we're solving for delta H of vaporization. All right, so our P1 is this guy, 100. This is our T1. This is our P2, and this is our T2. Okay, so we're going to put ln 760 over 100 millimeters of mercury is equal to X, which is our delta H of vaporization. That's what we don't know. R is given to you 8.31 joules per mole Kelvin. Now, T1 is related to P1. So this was P1, this is T1. So 34.9, we're going to have to convert that to Kelvin. Let's see, where's my number? Oh, I've just rounded it up to 308, so good enough. 1 over 308. So 34, rounded it up to 35, add 273, so 308, minus, now T2, I take my 78.4 and add 273 to it, and that's 351, 1 over 351 Kelvin. Okay, so we have everything that we need. Go ahead and do this first. So 760 divided by 100, and do the natural log of it. Like do this, 760 divided by 100, and then press ln for that number, and you will get 2.03. And then it's just algebra, guys. You should be able to handle algebra. A lot of people have difficulty with fractions. Don't let that trip you up. If I were you, I would go 1 divided by 308, press equals, and then minus, and then open parentheses, 1 divided by 351, close parentheses, and then press equals. You'll get that value. Once you have that value, take this multiplied by 2.03, so then it means this value will be something x, and then this times this, and then you divide by that number to get x and manipulate your thing, and you end up with 4.23 times 10 to the 4th joules per mole, or if you wanted to switch it to kilojoules, it would be 42.3 kilojoules per mole. All right, hopefully you can see all that. If you find that you are having trouble with algebraic manipulation, make sure you come and talk to me and I'll help you out. But again, I'm here not to teach you how to do algebra. I'm just here to teach you how to apply all of this, how to use algebra as a tool in chemistry. All right, so hopefully you're okay with all of that. Now, what some students will have difficulty with is the third type of problem where, let's say, this is the unknown. Okay, for that, same thing. It's just algebra that you're tripping up on. You'll know these two. So divide this by this, press ln, so you've got a number here. So, and you have this number, and you have this number, and you have this number. So the problem is that you have this x in the denominator. So put everything over on this side, and all you're going to have is this over here. And then just make sure you get this out of the denominator into the numerator. Again, algebra, and solve for x. So definitely doable, guys. Clausius-Clapeyron equation will definitely be on an exam. You'll probably have maybe 1 or 2 problems, maybe 3. I don't know how many, but you need to know how to do it. Just know the equation, know how to plug in the numbers, know how to use your calculator, and you should be all set. All right, the next thing we're going to do is a little different. We're going to talk about phase diagrams. And your book talks about lots of different complicated phase diagrams, but honestly, all I want you to know are the really simple ones. So I'll show you the type of thing I need you guys to know. So if you have something like this, temperature here, pressure here, and maybe something like this. Okay, so basically what this is telling me is that this is a phase diagram of a substance, all right? This is at this pressure and temperature, that substance is a solid. At this pressure and temperature, this substance is a liquid. And at this pressure and temperature, this substance is a gas, okay? So this is what a phase diagram does. It tells you at what pressure and what temperature that substance is either a solid, a liquid, or a gas. So this is under the big heading phase diagram. And like I said, the book has lots of different complicated phase diagrams. I'm just going to ask you to know this simple basic type, okay? There are there are several things you need to know about this. This line here, let's say AB, this represents melting point and freezing point, all right? So if you're going in this direction, you're melting. If you're going in this direction, you're freezing, okay? This line over here, say BC, this would be your boiling, condensation. Okay, so if you're going in this direction, that is your vaporizing, boiling it, or in this direction, you're condensing, okay? And then obviously solid to gas or gas to solid, that's your sublimation deposition, okay? This point over here, this is called the triple point. The triple point. That point, at this pressure and this temperature, all 3 states of matter exist in equilibrium. Okay, that's the triple point. At this point over here, this point, this is called the critical point. Critical point or the critical temperature. Any temperature above this, you only have gas. You can't have liquid anymore. So that's the critical temperature or critical point. Anything above this, doesn't matter what the pressure is, but anything above this, you cannot turn it into a liquid. It's a gas, okay? Those are the main things I want you to know on a phase diagram. Here's a real quick example. Carbon dioxide in steel cylinders is available as a liquid at room temperature, but oxygen is not available as a liquid. It's available as a gas at room temperature. Why is that the case? Well, the critical temperature of carbon dioxide is 31 degrees Celsius. So critical temperature, anything above 31 degrees Celsius, it can't exist as a liquid. Well, room temperature is 25. So that's why carbon dioxide can exist as a liquid in canisters, okay? At enough pressure, you can get it into a liquid. But oxygen's critical temperature is actually minus 119 degrees Celsius. These are not numbers you need to memorize, but I just want to show you that this is why we don't have canisters of liquid oxygen. We have canisters of gaseous oxygen, not liquid oxygen at room temperature. Okay? All right, so we can't liquefy oxygen at all, at any pressure, unless you're below negative 119 degrees Celsius. Okay, so the next videos will deal with intermolecular forces and their effects on vapor pressure and boiling point and viscosity and all sorts of good stuff. I'm trying to turn this off.